All right, let's dive right in. Today we're looking at what might be one of the most audacious, out there ideas in modern physics. It's a framework called mode identity theory. And believe it or not, this whole wild ride starts with a single, incredibly strange number. Take a look at this. It's a decimal point, followed by 121 zeros and then a 1. Now, this isn't just a tiny number. It's quite possibly the most bizarre and important clue in all of science. So, what is it? Well, this number is what we get when we actually measure the energy of empty space, the vacuum energy. The problem? Our best, most trusted theories in physics predict that the number should be, well, it should be 1. That gap, that chasm between what we predict and what we see, is a staggering 122 orders of magnitude. It's, no joke, the biggest error in the entire history of science. And that leads to the one giant question that has kept physicists up at night for decades. Why? Why is the universe so unbelievably empty? What mysterious force is canceling out all of that energy that our theories say should be there, canceling it out almost perfectly, but not quite?
To really get a grip on how deep this problem runs, we've got to rewind the clock about 100 years, all the way back to the man himself, Albert Einstein.
So, back in 1917, Einstein's equations suggested the universe should be collapsing or expanding, but he thought it was static. So he added a little fudge factor, called lambda, the cosmological constant, just to hold everything in place. Then, in 1929, Edwin Hubble proves the universe is expanding. Whoops! Einstein famously throws out lambda, calling it his biggest blunder. But then, fast forward all the way to 1998, astronomers discover something wild. The expansion isn't just happening, it's speeding up. And guess what they needed to explain it? Yup, good old lambda comes right back, this time with a cool new name, dark energy. We can measure it, but we have no idea why it's there. And this whole saga points to a much deeper crack in the foundations of physics. See, we have these two powerhouse theories. General relativity, which is brilliant for describing the big stuff, planets, galaxies, the whole cosmic dance. And then we have quantum mechanics, which is perfect for the tiny stuff, atoms, particles, all the weird quantum fuzziness. The problem is, when you try to make them work together, they just break. They produce mathematical gibberish. That crazy cosmological constant is just the most obvious symptom of this epic clash of titans.
So what if the problem isn't with the theories themselves? What if the problem is with our most basic assumption about the universe itself? This is where a radical new idea called mode identity theory steps in. It proposes a mind-bending solution that all starts with a single, simple claim about the shape of our universe. To get your head around it, think about a Möbius strip. You've probably made one before. You just take a strip of paper, give one end a single half twist, and then tape the ends together. All of a sudden, you have this bizarre object that only has one side and one edge. You can trace your finger along its surface, and you'll end up right back where you started, but on the other side. Except there is no other side. And that brings us to the absolute core of mode identity theory. Here's the postulate. Matter isn't really a particle. It's a wave that we're sampling at a certain point. And the universe itself has a shape, that weird one-sided Möbius strip shape, which is itself embedded in a four-dimensional sphere, or a hypersphere. Now here's the incredible consequence of that shape. Just like a guitar string can only vibrate at specific frequencies to make specific notes, the universe's unique topology forces a single fundamental wave to settle onto it. It's like a cosmic hum. And get this, the 13.8 billion years we call the age of the universe, that's not a countdown from a beginning, it's just where we are right now on this single giant cosmic wave. Okay, I know, that is a wild idea. A universe shaped like a twisted loop, humming one fundamental note. You might be thinking, so what? Well, the so what is what happens when you take this single, simple idea and you test it against the biggest, baddest, most unsolved mysteries in physics. And in the creator's own words, this is what happened next. Once the geometry of the universe was set, with absolutely zero fine-tuning or tweaking, the fundamental constants of nature, they just started falling out of the math. First on the chopping block, that ridiculous cosmological constant, the one that was off by 122 orders of magnitude. Well, mode identity theory derives it from first principles, no guessing. The theory's prediction is within 2% of the value we actually observe. The biggest error in the history of science, it just evaporates. So what is the cosmological constant? It's just the ground state hum of our Möbius-shaped universe. Problem solved. Check.
All right, what's next? The Hubble tension. This is a super weird problem where astronomers use two different methods to measure how fast the universe is expanding, and they keep getting two different answers. It's a huge headache. The theory predicts that any measurement taken from inside a galaxy, like ours, will be shifted by exactly 8.4%. And guess what? That shift perfectly explains the disagreement.
So the Hubble tension isn't a tension at all. It's just a local phase shift in the cosmic wave because of where we are. Simple. Boom! Then you have maybe the most famous number in all of physics, the fine structure constant, alpha. It's roughly 1 over 137, and for a century, nobody has had a clue why it has that specific value. Well, from that very same cosmic wave, the theory spits out a value for alpha that's accurate to within 0.5%. I mean, you gotta love the confidence here. Haters, eat your heart out. But it doesn't just stop with cosmic constants. The theory's geometry also generates predictions for the masses of the fundamental particles themselves, and the results are just stunning. Out of the 12 known fundamental matter particles, 10 of them land right in the ballpark, and 3 of them, the electron, the up quark, and the muon, are predicted with jaw-dropping accuracy. You know, this all connects back to one of the giants of physics, Louis de Broglie. He spent his entire career arguing that the wave was the true fundamental reality, not the particle. He never lived to see his ideas really take root. In a way, this theory is picking up that torch and finishing his work. Now, look, all of this sounds incredible, almost too good to be true. But a theory isn't science unless it can be tested, unless it can be broken. And this is where things get really, really exciting. Mode identity theory makes a very clear, very falsifiable prediction that is about to be put to the ultimate test. And that test has a hard deadline. In October 2026, the Euclid Space Telescope is scheduled to release its first major batch of data, which will give us the most detailed map of the distant universe we've ever had. So here's the showdown. The theory predicts that a specific value related to how galaxies rotate, something called the Mond acceleration, should actually change as you look further back in cosmic time. Standard cosmology, our current best model, says that value is a constant. It never changes. The predictions are polar opposites. There's no middle ground, and Euclid's data will be able to see which one is right. So what's the bottom line here? We have a theory built on one single, elegant geometric idea. No knobs to tune, no fudge factors. That seems to solve some of the deepest puzzles in physics, and it's facing a do-or-die prediction with a date stamped on it. As its creator puts it, come this fall, either this whole idea gets a giant fail sticker slapped on it, or our entire standard model of the universe is in for a serious, serious rewrite.